All right, well, if you watched the first video, then you got a little bit of introduction into how this stuff is going to work. What we're going to do now is actually work through that example with the trees. And so I'm going to get that data set opened up again, and then we will take a look at how we can use the procedures that I've outlined for you. There's if you grab your notes page, that would be great, because then you can take a look and see kind of what the procedures are that I'm going to be using. So, all right, let's share out the data set here again. All right. And as I mentioned, I'm going to do a confidence interval first. So the idea was in Georgia, this old growth forest, they're looking at the north and south parts of the forest. And how does the size of the pine trees in the northern part compare to the southern part? And they're doing the measurements of the diameter of the trees at a person standing there at your chest height. They just take a tape measure and they go around, and then they figure out the diameter. And so the first thing we want to do is come up with a confidence interval for the difference between north and south. And so I'm going to get my pen out here, and I'm going to be making a confidence interval for mu1 minus mu2, where mu1 is the population mean diameter in the south, and mu2 is the population mean diameter in the north. And I am going to go ahead and use mu1 and mu2. I could call it mu south and mu north. And then you wouldn't maybe have to write out so much here in terms of describing what you're going to do. So the first thing I'm going to do is check my conditions. And you don't have the text probably right in front of you. This is on page 635. But it does say that it was random sampling in the prompt. So we know that that's given. For the normal condition, since n1 is greater than 30, well, greater than or equal to 30, n2 is greater than or equal to 30, we know both, excuse me, both those populations, both those samples distributions are approximately normally distributed. And independent, well, this is a gigantic forest, so obviously we can assume there's more than 300 trees in the north and south. Also, because they're at opposite ends of the park, we can assume that they are independent of one another. So 10% rule is going to work for individually, that they are sampling in an independent fashion from their population. And then independent sampling is because this was a totally different sample from the north and the south. So my confidence level is given in this problem at 90%. So I'm not given any flexibility here for that. So we'll just have to go with what they gave us there. I know that sometimes you want to be able to choose your own, and they didn't really give us the option this time, so that's a bummer. But I think you're used to that. That happens a fair amount. So I'm not going to but usually that's not one of the things that they allow you to choose. And I think you saw that previously. So, all right. The next thing we're going to do is get our point estimate and then get our critical value T star. Oh, sorry, my mouse is kind of freaked out here. I'm encoding a file, a video, the first video from this at the same time. It's all of a sudden really slowed down. Okay, so sorry. The point estimate is going to be x1 bar minus x2 bar. Well, in this case, x1 bar is 34.53. X2 bar is 23.7. You can see that right here. So if we, let's see, subtract those, we get 10.83. Like so. And then we're going to come up with our margin of error. And to get that right, we're going to do T star times the square root. I'm going to take S1 over N1, S2 squared over N2. Whoops, I wrote N2, sorry. I meant 30. You know what I meant. And, oh, come on. There we go. And that's how we're going to get our margin of error. Now, in this case, since the ends are the same, I know my degrees of freedom is going to be 29. And so I'm just going to go to a table for the T distribution. 29 degrees freedom, look for the column for 90% confidence, and that'll be our T star. So let's see if I share you the table. What happens? Do we lose our work? I hope not. Oh man, I hope we didn't just lose all of our work. I'll recreate it if we did. I just want to show you that for where we are on the table, 90% confidence is this column here, and our degrees of freedom is 29. So 29 degrees of freedom, 90% confidence. Our T star is 1.699. So, oh, I hope our work is still there when we go back. It's not. Sorry, guys. Still learning this whole Zoom thing. I'm gonna there we go. Margin of error. Well, now we know will be 1.699 times the square root of 14.26 squared over 30 plus 17.5 squared over 30. And that should give us a margin of error of 7.00. So finally, our 90% interval is 3.83. And then the upper is 17.3. All right, so there's the confidence interval. Notice the entire interval is positive. So the fact that 0 is not even in there tells me that this is going to be pretty much statistically significant automatically. So if I was trying to do the significance test, the null hypothesis would be that mu1 minus mu2 is 0. The alternate would be that mu1 minus mu2 is maybe greater than 0 in this case, or not 0. But I know that that's going to turn out to have a small p-value because I can already see that it is significant with a 90% confidence interval because 0 is not included. So, all right. Well, I believe, let me just double check something really quickly. That is our example. And your homework that's coming up here. I don't know why I can't find my assignment calendar here. I had it open earlier. Oh, I know why. I'm still presenting the other thing. There it is. All right. So the first part of the assignment deals with comparing two means through confidence intervals. And so you'll be making a 90% confidence interval. And then we'll do significance testing on Thursday. All right. Well, hope everybody's doing well. And I will have another video out for you on Thursday on significance testing for these two means. And then on Friday, I'll be around to answer questions starting around 10:30, but like I said, might be a little bit late. Okay. All right. Bye, everybody.